Okay, I think I got my video recorder fixed now, but this is going to be a 5.2C, but it all adds up to about 30 minutes is the goal. So more log properties. I have 3 more here. This would be the sum, and then the difference, and then this is called the product. And if we just kind of go over these, kind of like exponential, if you think it's an inverse of exponential, very similar. If you're multiplying 2 things of a log of 2 things, and it's being multiplied, you would convert it to adding them separately. If it's dividing, you would convert it to subtracting them separately. And then this one here is the product power, or power, it's actually product, but I call it the power, because if you have a log raised to a power, you can bring that power down in front and multiply it. That's where the product part comes in. That's how you solve. This one here is the key to solving where the exponent, so you could have 5 to the x, where the exponent is the variable. Okay? So let's go ahead and try some actual problems after we got through all these properties. Rewrite each expression as a sum, difference, or product of the log, and then cite by the number which one you're using. So this first one here is subtracting. Oops, I'm sorry, not subtracting. That's a very common mistake what I just made here. It's actually multiplying. It's the log base 4 of 5 times x minus 7. And so when you're multiplying, you're going to change it to adding. To separate those logs, to separate out into 2 logs, we want to put this one as a sum because we're multiplying. So this is going to be log base 4 of 5 plus log base 4 of x minus 7. And this is number 6 from the previous screen. The next one here is dividing. So we're going to want to convert to subtracting. If we're going to want to separate those into 2 logs, we do the log of x minus 8 minus the log of x, and that is number 7. Moving on to the next one, rewrite each expression as a sum, difference, or product. Same thing. So this one here, again, it's multiplying. So we're going to take the log of e squared plus the natural log of e plus 3, and that's using number 6. And then the second one is number 8, which is the product one. And you can bring this 6 down in front of the log. So it's going to be 6 log base 4 of y. And you could put a multiplying there if you wanted to. Usually you typically don't see that in there. Okay, another example. The population of Japan for the years 1984 to 2006 is approximated by this log function. And this is in millions of people, with x equal to the number of years after 1980. According to this model, what is the estimated population in 2000? So I would go 2000 minus 1980, and I'm going to get to x equals 20. So I'm going to take that 20 and I'm going to drop it in right there. And this is in millions of people, right? And then I'm going to go to my calculator. And just so you can see where everything is on your calculator, I'm going to say 114.016 plus, and I'm going to do the natural log of 20. I'm going to get, mine didn't have the 4 here, so I just redid it. and I would get 126.79. You could keep going because this is in millions if you wanted to, but I think we're going to end it at 126.79 million people would be my final answer there. What do you think is the natural disaster that causes the highest fatalities? And there's a lot of fatalities out there caused by natural disasters, but here's one from 1970 to 2004. Just to take a look at that, it's kind of interesting. And if you look at it, heat or drought ends up to be the largest one, followed right behind it by these two. Would be the largest or the most deaths. And just to look at some other data, which is pretty interesting. We are going to do the Richter scale. So we're going to take one of the natural disasters of earthquakes, and we are going to figure out the Richter scale of this. So the Richter scale, because the intensities of earthquakes are so large, the Richter scale was developed to provide a scaled-down measuring simpling system, right, that permits earthquakes to be more easily measured and compared. And this is in your book too, but this is the formula for Richter scales right here. And this is the magnitude, so I'm going to tell you what each of these mean. This is the magnitude of the earthquake equals the log of I, this is the intensity of the earthquake, divided by I naught. Which is certain minimal intensity used for comparison. So in other words, if nothing's happening and there's no earthquakes, there is a minimal movement in our Earth, right, rotating, that's happening that you can't feel. If you just stood there right now to try to feel the Earth moving, it wouldn't be moving. But it is moving, but it's so slow you don't feel it. So that's why we're dividing it by the I naught. Which is another way to say the initial intensity of the Earth moving. Okay, so couple things to make this simple. Either you're going to be finding the R or the I. So either I'm just going to rewrite this. Either you will be finding the R, or I'll just rewrite this again. So it's basically given one of the variables, there's a Richter scale variable or an intensity variable, and either you're going to be asked to find the R given the I, or you're going to be asked to find the I given the R. So you're going to be able to input the I and come out with the R, or you're going to input the R and come out with the I. So thinking about it that way, those are the two options for any of these. So we just have to decide which one we're given, plug it in, and find the other. So here's our first question here. If an earthquake has an intensity of 250 times I naught, what is the magnitude of the Earth? So in this one right here, I'm going to just rewrite my formula up here. So this one right here, I'm given the intensity, and I am trying to find the magnitude. So I'm going to put this in, so that many times I naught. So if I'm going to rewrite this, it's going to be the log of 250,000 times I naught over I naught. And notice every time these will cancel out. So then you're just going to have the log of 250,000, which ends up to be, and we round these to the nearest tenth, so this should sound really familiar, 5.4 on the Richter scale. So that earthquake was 5.4 on the Richter scale. So the Richter scale measurements for the San Francisco earthquake that occurred in 1906 was 8.25. Find the intensity of this earthquake as a multiple of I naught. So if I was doing this one, again, I'm going to rewrite my Richter scale. So it's like a formula to figure it out. And I'm given on this one the Richter scale, and they want us to find the I. That's what they're doing on that one. So on this one, I'm going to put the 8.25 here. And in order to solve this one, the only way to solve it is by changing it to exponential. So this log has a base 10. So I'm going to say 10 to the 8.25 equals I. And there's an I naught in here, so in the intensity of this earthquake times a multiple of I naught. So the I naughts should always cancel out, so I'm not super concerned about that. And if you were to put that on your calculator, you're going to get a really big number. So we're in the millions here, right? Because this is thousands and hundreds. So that's how many million times intensified from the, and you could put the I naught on here if you want, from the original intensity of just the earth moving. So that's a really big number. And that's why these are done as like 8.25. It helps you understand. That means that's the intensity of the earth moving. All right, and then we're getting into our word problems, which we will be working on in class.